Here we are, the last part of this exam to review, part 4, improper integrals, okay? So remember, when we have an improper integral, that's one where we integrate, say, to infinity, to minus infinity, or to or through a discontinuity of a function, okay? So it's not necessarily a technique of integration, it's just a class of integrals that we have to worry about. And so we look at this first one here, we have the integral from 0 to infinity of 1 over x plus 1 squared times x plus 2. But you look at that and say, that's not an improper integral. Well, it actually is, okay? This is a so called type 1 integral, okay, where we integrate to or through infinity or minus infinity even. And so we need to interpret the integral symbol here. This needs to get interpreted as the limit as t approaches infinity of this integral from 0 to t. We're allowing that upper boundary to go out to infinity. We're just going to see what happens. Now, of course, if we look at the integrand, we see it's a proper rational function. And so what should we be thinking going off in our head? Partial fractions. Okay, so we need to do a partial fraction decomposition here. And hopefully we've seen it enough times. Okay, please go back and watch the partial fraction series on how to handle those. So we do our decomposition here. For our repeated linear factor of x plus 1, we write it down twice, with the second one getting a power of 2, both numerators being constants here. And then we have the lone factor of x plus 2. Okay. And now we're going to go ahead and multiply through, clear the fractions to set up. So when we do that, when we multiply through, and let's just do that for completeness here, show what we multiply by. We multiply by x plus 1 squared times x plus 2. Okay, we have 1 equals a times, looks like we get x plus 1 times x plus 2. Then plus b times x plus 2. And then plus c times x plus 1 squared. Okay? And now we're going to go ahead and choose your clever x values here. The first clever one that I would choose here, or of course, you can go ahead and set up a system of linear equations, okay? Whichever one works for you. I'll choose x equals -1 here. So all my x plus 1 terms will vanish. Left-hand side is independent of x, so we just have 1 equals, and now on the right, my a and c terms vanish because they have an x plus 1. Okay, if I put that into the middle term for b, 2 minus 1 is 1, so b is equal to 1. Hey, not a lot of work, right? All right. If x is equal to -2, that's the next clever value I can choose here. Left-hand side's independent of x. Okay, if we had an x on the other side, we'd have to plug that in there as well. Okay. On the right, all my x plus 2 terms will vanish. So I have x plus 1 square left over for the c term. -2 plus 1, okay, is -1. Squared is a positive 1. That gives me 1 is equal to c. Well, that's just nice, right? Okay, and then what do we do for the last one? Choose any other x value that you want. I'll choose x equals 0 here. It just makes things a little nicer. Let's write down what we get here. 1 on the left, and on the right, okay, I'll get 2a, okay, plus 2b plus c. Okay, I know what b and c are. I just need to find out what a is. Okay, well, b is equal to 1, c is equal to 1. So we have 1 is equal to 2a plus 2 plus 1. Okay, if I shuffle some things over, okay, we will get that, well, we get that -2 equals to 2a. And so that tells us that a is equal to -1. Okay, so that part was just the partial fractions bit here. Let's just double check our notes here to make sure that we got everything right. And everything looks good. So I did not make a mistake. Okay. Now, what do we do? The same thing. We're going to go ahead and look at this integral here. So originally we had the integral from 0 to infinity of 1 over x plus 1 squared times x plus 2, okay, dx. Okay, and now remember, since this is an improper integral, we're going to treat the integral sign as a limit here. So it's the limit as t approaches infinity of this integral from 0 to t of, well, I just take my little recipe here. Okay, copy. Whoops, that's not good. Copy, there we go. Paste, Nope. Try it again. Copy, paste. Okay. All right. Now we replace where the weights. A is equal to -1. B and C are both 1. All right. So now we just handle this integral. Okay. Now, some of you may already see the punchline, but don't spoil it for everyone else, okay? Let's go ahead and look at the antiderivative here. Okay. So we have the limit as t approaches infinity of minus log of absolute x plus 1. Okay. Second term, we have a minus 1 over x plus 1. Okay, that's good. Okay, and then we have a plus log of absolute x plus 2. We're going to evaluate this on the boundary from t to 0 and then take the limits. Well, okay. Just for kicks, let's go ahead and plug everything in. So the limit as t approaches infinity, we have, let's see, minus log of absolute t plus 1, minus 1 over t plus 1, plus log of absolute t plus 2. Okay, nothing really new there. And now minus the evaluation at 0. Okay, so I'll go ahead and kind of skirt some of this here. Okay, so we'll have minus, okay, 0 plus 1 is 1, and the log of 1 is 0, so that first term is gone. Plug in 0 into the second term, I get a -1. And then in the third term, I just get a log 2, okay? Then, of course, I'm going to take the limits. But I won't really have to do much because take a look here, okay? Notice that while this term here in the middle, this 1 over t plus 1, that's going to go to infinity as t, excuse me, that's going to go to 0 as t goes to infinity, okay? If I divide by a bigger and bigger number, I'm going to get a smaller and smaller number. So while that one goes to 0, take a look at the other two terms on the ends here. Well, log is an increasing function, okay? So this one here, this log of t plus 2, that goes to infinity, and this one's going to go to minus infinity. But Sean, infinity minus infinity is 0. No, don't say that. No way, no how, pal. Okay? Infinity minus infinity is not 0. But here's the big problem, okay? You have one term that fails, okay? One term that increases without bound. So the problem is this limit is infinite, okay? Because one term fails. This fails to converge. So the integral is divergent. So for improper integrals, okay, if one of the integrals fails to converge, if you have a sum of improper integrals, okay, if one of the integrals fails to converge, the entire integral fails to converge. Okay, because that one I've bracketed down there fails to converge, the entire thing fails to converge. We're done. We don't have to do anything else. Okay. So this integral diverges. And now let's take a look at this other one here. All right, so we're integrating from 2 to 6, x over square root x minus 2 dx. And this one is a little different, okay? This one's actually a type 2 integral. Okay, why is it type 2? It's type 2 because now if we look at this, if I plug in 2 into the function here, notice in the denominator I get a 0. Okay, there's a discontinuity at x equals 2. So this is a type 2 integral, and I have to figure out how to handle this. So one of the first things I'll do here is I'll go ahead and make a change of variable, okay? We're going to go ahead and set u equal to x minus 2. So du is equal to dx, okay? You'll see why I'm doing this in a second. And then, of course, with u equals x plus 2, that means x is equal to u plus 2. Okay. And now, of course, we change the limits, okay? When x is equal to 2, u is equal to 0. When x is equal to 6, u is equal to 4. Okay, so what goes on here? So our original integral gets transformed into something a little more manageable. Okay, you will see why I've done this here. So it's an integral from 0 to 4 of u plus 2. Let's fix that, okay? U plus 2, fix that, over the square root of u du. Okay? Well, why did I do that? Well, because I can break this up into two simpler parts. Okay, we've seen integrals like this before. All right, remember when I have a fraction and I have stuff over common denominator, I can just like separate. Okay, how do we add and subtract fractions? That's the main question I always ask you. Okay, now let me go ahead and fix that upper limit here. Okay, we have the discontinuity now moved at 0. Okay, but I'm going to be approaching it from instead the positive direction from the right. Okay, you can draw the picture here. So this is going to be now interpreted as the limit as t approaches 0 plus, okay? 0 from the right, okay? We're coming at it from above, all right? This is the integral from t to 4. And now I'm just going to go ahead and separate the fraction here, okay? So u over square root u plus 2 over square root u, okay? Now, if we just ignore the limit for a second, okay, nothing really changes here, okay? But we still have to write it down. It's part of our problem. Now, notice here, u over the square root of u, okay? We're just dividing with exponents, okay? U divided by u to the 1/2. That's a u to the 1/2, a square root of u. And I still have this here. All right. And now you just use your power rule again, okay? That's all we're doing here. So we have this limit here. Okay, take the antiderivative of square root u, that's u to the 1/2. So we add 1, u to the 3/2. Divided by 3/2, that's multiplying by 2/3. And then plus 4 square root u, okay? U to the 1/2 divided by 1/2. Dividing by 1/2 is multiplying by 2. 2 by times 2 is 4. Okay, and now we're going to go ahead and evaluate here on the boundary. Okay, and you'll see something here. So let's go ahead and write down the evaluation steps. So 2/3 times 4 to the 3/2, okay, plus 4 square root 4. Okay, now minus 2/3 t to the 3/2 plus 4 square root of t. Okay, now we're coming at this from above, okay? So we're doing this as t gets smaller from the positive direction, okay? Now, you can kind of skirt this a little, okay? It's safe to plug in t equals 0 here, okay? And I need to close this off. Okay, so when I plug in t equals 0, notice that both these terms, okay, both those terms go to 0, all right? And so what am I left with? I'm just now left with the remaining stuff there in the first two terms. Okay, we have 2/3 times 4 to the 3/2 plus 4 times the square root of 4. Well, square root of 4 is 2. 4 times 2 is 8. And if you want, you can also go ahead and simplify this a little because remember that x to the 3 over 2, let's make that a different color real quick. X to the 3 over 2 is the same as x times the square root of x. So if you want to, you can write this as 2/3 times 4 square root of 4 plus 8. Okay, well, 4 times the square root of 4. Okay, well, we saw that there, okay? Square root of 4 is 2. 2 times 4 is 8. Then 8 times 2 is 16. So 16 over 3 plus 8. And if you like, put it all over the same fraction. So 8 is 24 over 3. So this is 40 over 3. Okay. If you write this one down or this one, those are both the same answer. Okay, so we now handle our limit. Okay, once again, noting that both of these terms here, okay, encompassed by the magenta crossouts, okay, they go to 0 as t goes to 0 plus. All right. Now we're come to the comparison theorem. Okay, we don't want to actually evaluate these integrals, but we want to see if these integrals converge or not. Okay, so we're not actually going to evaluate them. Okay, now watch that last part of the improper integrals video. We're going to invoke the comparison theorem, and here's what that is. Okay. So I'll just give a quick recap here. So suppose f is less than or equal to g, okay? If this infinite integral, okay, of f, okay, if this integral diverges, and let me make this a little better. So if this integral diverges, then the bigger integral, the integral of g, also diverges. Okay, now we have the other direction. Okay, if the integral of the bigger one, if the integral of g is convergent, then the integral of the smaller converges. Okay, so we're actually not going to evaluate these integrals, but we're going to use some basic inequalities here. Okay, and one of the basic inequalities here is this reciprocal property. Okay, so we're going to make a note here. Okay, if I have, and I'll make this kind of simple here, if 1 over a, sorry, if a is less than b, then when I take reciprocals, I'm actually flipping the direction of the inequality, okay? So if a is smaller than b, then 1 over a is bigger than 1 over b. Making the denominator of a fraction bigger makes the whole fraction smaller, okay? So we're going to remember that, okay? Making the denominator of a fraction bigger makes the entire fraction smaller. And we're actually going to use this to our advantage, okay? Because if we didn't have that plus 2 there in this integral, well, we'd be home free, right? But we do. So we need to find a way to remove that. What I'm going to do is make this fraction in a way bigger or smaller, okay, in order to force something that's more manageable. So we're going to look at this here. So notice that if I compare x to the fifth and x to the fifth plus 2, well, x to the fifth plus 2 is always bigger, right? I'm just adding 2. So when I have this, and I take reciprocals just by the above property, 1 over x to the fifth is actually now bigger than 1 over x to the fifth plus 2. Okay? And so, and it follows, I can multiply both sides by x cubed. Okay? So what I'm going to do here is I'm going to replace the denominator of that fraction. Okay? So here's what we're going to use. We have this integral, x cubed over x to the fifth plus 2. Okay? I'm now going to make the denominator of the fraction smaller. Excuse me, I'm going to make the denominator, yes, I'm going to make the denominator smaller, okay, which makes the fraction bigger, okay? So this whole thing is less than or equal to, okay, the integral from 1 to infinity of x cubed over x to the fifth dx, okay, and this follows by monotonicity of the integral, okay? Well, x cubed over x to the fifth, I can simplify that, right? 1 over x squared dx, okay? And this is our basic family of p integrals, okay? We'll come back to this when we talk about p sequences and p series, okay? But without doing much work, you can tell that this one converges. But if you needed to, right, okay, you can go ahead and write the limit process. You take an antiderivative, right? Okay, and then you see that this guy actually converges to 1. So the integral converges by comparison. Whoops. If only I could spell, right? The integral converges. And it converges by comparison. Okay, we didn't actually find the value of the integral, but rather we went ahead and found an upper bound for it, okay? That's what we're doing here, okay? So we have to use these inequalities here to sort of massage your way through, okay? And it does take a little bit of practice, okay? We'll need this again when we talk about the direct comparison test for infinite series, okay? Now, this one here is a little funkier here. Sine of x plus 2 over square root of x. We're integrating from 1 to infinity. And we have our basic estimate here for the sine function here. Okay, and it's that the sine of x is bounded between 1 and -1. And in fact, the tool that we're going to use here, because I have a hunch that this integral diverges, we're actually going to go ahead and use that part of just shaded in yellow. Okay, so why does that work? Okay, well, if we didn't have, the sine x there, I'd have a 2 over square root x. Well, take an antiderivative. Okay, so what's that? 4 square root x, okay? And then we take the limit. Well, square root is increasing. That's the problem. Okay, so we're going to go ahead and replace sine of x from below with a -1. So here's how we're going to write that. We have this integral, and I'll go ahead and shuffle the term order here. Doesn't matter because addition commutes. Okay, this is greater than or equal to the integral from 1 to infinity of, well, I'm going to go ahead and replace, okay, and just to make it more clear here, I'll write it like this. Sine of x is greater than or equal to minus 1, and that holds for all real x. So I'm going to replace that with a 2 minus 1 over square root x dx. Okay, now I just do my usual thing, right? Okay, this is a limits process. T goes to infinity. Okay, now we take the antiderivative. 1 over the square root of x, that's x to the 1/2. Okay, when you do your power rule stuff, that's 2 times square root x. And you should immediately notice a problem here, okay? We're looking at this limit here, but square root is increasing. So as I put in bigger and bigger numbers, the square root is still going to be a big number. So this goes to infinity. And because the smaller integral diverged, the bigger integral also diverges. So the results here, our conclusion, the integral diverges by comparison. Okay. So we need to remember this fact, okay, for the comparison theorem, because it's going to carry over for when we talk about infinite series. It's the same thing, just something counting measure. But the idea is if I can order two functions and I know that the smaller one diverges, the bigger one has to diverge as well. And if the bigger one converges, well, the smaller one can only be as large, so it has no choice but to converge, okay? So if you can control the smaller one and make it bounded above by a convergent integral, then the smaller integral converges. If the smaller integral diverges, the bigger integral diverges, okay? Don't get these mixed up. It's very easy to, all right? Well, that's it for chapter 3. You now have your techniques of integration. We've done a lot of practice, okay? We also just reviewed here in this video, okay? If you need an in-depth explanation, please go back and watch the corresponding videos or even watch my older videos as well, okay? When we return, we're going to take a little detour. We're going to talk about sequences and series because this is going to help us to understand series of functions, sequences of functions, okay? What does that mean? I won't say much for now. I'll see you in the next one.